Okay, let's go ahead and get started. So Friday we did the merge sort algorithm, and I think it's important that everybody see at least one n log n sorting algorithm. So that's why I think Friday was an important lecture for everybody. But today we're doing an optional lecture on Quicksort. Too bad that this isn't something that we always fit in, or it's not something that I would consider to be a required lecture. In the olden days, we would have done that. We might have had an exam question where we asked you about different sorting routines. I've heard people make the analogy that if you're studying literature, then maybe there's certain great works of literature you're supposed to be familiar with, some Shakespearean plays, for example. In computer science, kind of the equivalent, the classics for us are often algorithms. And Quicksort would certainly be in that category of probably one of the most commonly used algorithms, if not the most commonly used algorithm in the world, because it's a very fast sorting routine, and sorting is something that people often want to do. So anyway, we're going to go over that today. Our question of the day last time was about one of these questions about is water wet, kind of one of these fun things that we can see what people think. So that was the result for that. So what I'm going to do is talk about the Quicksort algorithm, develop the code with you, and then I'm going to talk a little more about this idea of the stable sort that I mentioned at the end of Friday's lecture, because I think that's a useful thing to understand. My guess, I talked about it, but it went a little bit quickly. So we'll spend a little more time talking about that. So what I've done for Quicksort, so in Friday's lecture when we were doing the merge sort, I manipulated queues. You have this midterm that you're working on now, and so it was nice to talk about queues. I also did it with strings so that it was a more general purpose kind of sorting routine that would deal with, remember we had to call a compare to method in order to be able to compare the strings. Here I'm going back to, let's just do ints, simple ints, and I have them in an array. So what I do is I set up an array, I think this is 50 million. I set up an array of 50 million values, and I want to sort it, and I run the built-in sort against our sorting routine. Let me go ahead and compile and run this version. And this is going to be the same thing we saw last time, is that our Quicksort finished instantaneously, which was infinitely faster than the original, but that's because we haven't written it yet. And it ended up saying that the lists don't match. So it had some code that makes sure that we got it right. So I've got a version here of the sort. This is a common thing. You'll see this in the Java class libraries, that in the arrays class, there are a bunch of different sort methods, and they have kind of a different parameter passing. So you can pass it just an array of int, in which case it's supposed to sort the entire array, but there's a version of it that takes a low and a high. So I think I have a picture for that. That this is a common thing that we're going to be doing, that you want to sort not an entire array, but some portion of an array. So you provide a low index and a high index to say, I want you to sort that sequence, that kind of set of things in between. This is the one that we're going to write. The overall one just calls this using the entire array. 0 for the start index, for the low index, and length -1 for the high index. That just does the entire array by calling this method. So this is what we're supposed to write. I've included here a swap method. At the end of the 142 class, I talk about how we can't write a swap that takes two ints and swaps them. This has to do with value semantics. But what you can do is you can write something that takes, say, an array and two indexes. So I basically have a swapping routine where I say, in this array, these two indexes, I want you to exchange the values, because we're going to be doing some swapping tasks. So it's nice to have a method available to us that'll do that for us. Now, Quicksort, I mentioned the idea last time. Let me say a little bit about it. I didn't bring my cards today, but let me just kind of talk about it a little bit. Let me actually mention a different way, a different place. This is something that actually often happens to us. is that we find ourselves, so suppose you've got a stack of midterms, so maybe you've got something like, 200 midterms that are stacked here, and you want to say put them into alphabetical order. How would you put these 200 tests into alphabetical order? Well, you could use the insertion sort or the selection sort that we talked about. From Friday's lecture, you'd kind of know that a good strategy would be to divide the pile into two halves and then sort each half and then do the merging operation. That's actually beneficial. That would speed up your task if you had a pile of 200 tests to do. And then when you have your pile of 100 over here and your pile of 100 over here, splitting the pile of 100 into two piles of 50 is helpful as well. So, merge sort, it can be helpful at several levels there. At some point, you might get a small enough number of tests that you just put them into sorted order using one of the other sorting routines like insertion sort or something. I mentioned the idea of the quicksort, and this is something that I actually do when I have a pile, say, of 200 tests, is that I know something about the alphabet, and so what I tend to do is I tend to say, well, it's about evenly split. A to L and M to Z is kind of how I would split the alphabet. So what you can do is you can go through this pile of tests, instead of just doing a simple split, where you put half of them over here and half of them over here. You go through all of your tests and you see whether the last name begins with A through L or whether it begins with M through Z. So you kind of, put the tests into the two different piles. So you've got the A through L over here, the M through Z over here. And you could do that trick one level further. Like you could take the A to L pile and split it into A to F, G to L. You could kind of do some further splits like that if you wanted to. But in any event, if we get the A to L pile sorted and we get the M to Z pile sorted, then there's no merging operation because all of these A through L tests come before the M to Z tests. So we just put the two piles one on top of the other and we'd be done. So that's quicksort. That's kind of the idea of quicksort, is that we're using some value that's known as the pivot as a way of putting things in one pile or the other pile. We sometimes refer to that as partitioning this into two different partitions. In this, in the example I was giving, A through L and M through Z are the two different partitions. So, sometimes when people do a lecture like this and they have a live audience, they'll do a non-programming example where they're, say, going to sort people by height. So you get a bunch of volunteers to come forward, and you pick somebody from the crowd who looks like they're around middle height. So you pick somebody like that, and you have all the other people come up, and you see whether they're taller or shorter. If they're taller than this person, they go over here in this partition. If they're shorter, they go over here into this partition. So we split the people into people who are shorter than this person, people who are taller than this person. Then if we put these people into sorted order and these people into sorted order with that the pivot person in the middle, then we've got kind of a nice, already sorted. We don't have to do anything beyond sorting this group over here, this partition, and sorting this partition over here. That's the nice thing about quicksort versus merge sort, is that there's no merging operation. Okay, so that's the idea. So the real work for quicksort is public static void is involved in writing a method that I'm going to call partition. So just like I did here, where I kind of specified an array to sort and a low and a high, so that way it's general purpose and can sort not just the entire array, but any kind of portion of the array. I'm going to do the same thing here, that I want to be able to partition and give it a part of the array, not the entire array. So I have my integer array list, an int low and an int high. And if I was... well, you'll see this in the version that I put on the calendar for today. I mean, I put comments that describe, the fact that we want to partition the values using, thinking of that picture right here, that the low and the high are specifying a range of values that we want to be working with. All right, so we want to split it into two partitions relative to some pivot value. Well, so what do we do for our pivot? There's a lot of interesting theory, a lot of practical issues involved in the selection of the pivot. Well, so basically we've got this range of values in here, and we want to pick something. I said that when we were doing heights, we'd want to pick someone who's kind of in the middle of the pack in terms of height. When we were doing the A through L and the M through Z, I knew to kind of divide the alphabet, using that M value, things that come before M and things that are M or greater was kind of the way that I was pivoting in that case. Here I got to pick something that I can use as a pivot value, and it's really important what ends up happening in terms of this choice. So you could imagine that I would pick the low value. I just pick the first thing and say that's going to be my pivot. One of the things to think about is what would be an unfortunate choice for that pivot value? What would be something that would be problematic for us if we ended up picking it? I mean, the whole point is that we're trying to partition into two things that are less than that pivot, things that are greater than that pivot. And so we want something that's in the middle. We want something that kind of splits it in half is what we're hoping for. The worst possible value would be something that doesn't do any splitting at all. So for example, what if this array was in sorted order? What if it's already in sorted order and we make a call where we pass it something that's in sorted order? You might think that doesn't happen very often, but actually it does happen often. I mean, I think of it as things like, I use a database program or something, and it gives me the ability to put something in a sorted order, and a phone call interrupts me, or I go and take a snack or something like that, and I come back and I can't remember whether I sorted it or not, so I sort it again. We often sort a sorted list. So you don't want it to be really slow when you ask it to sort something that's already in sorted order. But what would happen, suppose we have the numbers 1 through 10 or something like that. If we pick 1 as our pivot, then there's nothing less than 1. So what we end up doing is kind of having the pivot value of 1, and everything else is in the second partition. So we didn't do any splitting at all. We only ended up dealing with 1 value. And then if we again kind of chose, say, 2 as our next pivot, then we've already dealt with 1, so now there's nothing that's less than the pivot, and so everything ends up in the second partition. We end up with something that's as bad as insertion sort or selection sort. It ends up becoming an n-squared algorithm, like those slow algorithms we discussed last time. So Quicksort can fall apart if you have a poor choice of the pivot. If the pivot doesn't do a good job of splitting, then we end up with a bad situation. Normally, if I have an audience, I ask people, so sometimes people might say, take the high value instead of taking the low value, but that would be just as bad if it was in sorted order. Often what I get as a suggestion from people is to take the value in the middle. So you could kind of take low plus high over 2, kind of the middle index. And that's not a bad choice for pivot. That would deal with the case where it's in sorted order. Actually, it would be picking almost a perfect pivot in that case, because it would be picking the thing that's in the middle. So that's a possibility. If you read about Quicksort, you'll find that there's lots of different theory that's been used, lots of different algorithms, different approaches. One of the approaches that's a common approach is what's called median of 3. So you look at the value at the beginning, you look at the value at the end, you look at the value in the middle. That's 3 different values to consider, and you take the middle one of those 3, median of 3. So that's kind of another approach that's sometimes used. So there's many of these things we could do. I actually wanted to mention a different idea about this. There's an interesting issue about Quicksort, which is, so that it can fall apart. The question is, how likely is it to fall apart? Like, what if you took the middle value? Then that seems like, that's going to deal with the case where it's in sorted order or reverse sorted order, which is one of those common ones that would make it fall apart. So maybe you get a bad pivot value once, but then, the odds that you're going to get a bad pivot value over and over and over and over again are not necessarily that great if you have things in a somewhat randomized order. But one of the things that I think is an interesting case to think about is, what if someone was a kind of hacker? What if someone was trying to make your code run badly? So the Sun Microsystems people years ago, and Oracle has continued this tradition, they published the Java source code. And Microsoft kind of felt obliged to publish the C# source code. So you can get the source code for the sorting routines that are used by Java and .NET. And so if it used, say, something like the middle value, somebody who was malicious could construct a very large sequence, and if your algorithm always picks exactly in a certain way, they could construct a case that makes it fall apart, that does an n-squared type sorting routine. And if it's a gigantic thing to sort, I mean, they could kind of lock up one of your servers by giving it some gigantic sequence to sort and putting it in just the right order to bring your Quicksort to its knees. So there's kind of something to be said for not being predictable. So how do you, unpredictable? Well, algorithms are predictable, but we've talked about the idea of randomness, that could you somehow use randomness. So I'm gonna introduce a variable spot, because the computation of it is complicated enough that I'll put it in a variable, put it on its own line of code. This is an index. I'm trying to pick a spot. And so suppose that I wanted to pick a random spot between low and high. So I just want to randomly pick from among these different possible indexes here, some random spot. You could imagine making a random object and calling r.nextInt. This thing is going to be called a lot, though, so I don't want to be constructing a lot of random objects over and over and over again. I mean, I could construct it once and pass it as a parameter, but that complicates things too. I kind of don't want to use a random object for this. The math class has something called math.random, and it has the property that 0 is less than or equal to math.random, which is strictly less than 1. It gives a value between 0 and 1, always strictly less than 1. We saw this in the Guitar Hero program. This is what next double returns, is something in this range. So the math class has a method like this that it can call. The math class sets up its own random object, and it sets it up only once, which is good. So that'll be kind of a simpler thing to use. So how do we turn this value between 0 and 1 into some integer? Well, so suppose we multiplied by 10. Then we're going to get a number in a range of 0 and strictly less than 10. But it's going to be a double, not an int. So we'd have to cast to int. If we did this would kind of chop off anything after the decimal point. This would get us a random integer between 0 and 9. It wouldn't give us 10, right? Because it's always strictly less than 1. So it never quite gets all the way up to that 10. So that would be an expression we could use that would get us a random integer between 0 and 9. Well, what we're looking for is a random integer that's at least low. So like the lowest possible index we'd ever want to construct, ever choose, would be the index low. So let's include that in our little expression here. So we want it to be at least low, but then this expression we're forming with math.random could be 0. That would be okay for it to be 0, because then we'd pick this index, or it could be 1 or 2 or 3. Well, how far away is this index right there? That index is not 10 away, it's high minus low. Kind of the right expression. If you think this could be as big as high minus low, if you add in low, then that means then the plus low here and the minus low here cancel, and it could be as big as high. But remember that this is always strictly less than that. So it never gets you. The highest it would get you is 1 less than high minus low. So it wouldn't quite. I mean, it would get you all of the indexes up to this index right here, but it wouldn't allow you to get to this spot itself. So in order to make that work right, we would do a +1. So, and actually, you know, the funny thing is, I think coming up with this little expression we have here using math.random and everything, this is almost the most complicated thing we're going to do in writing the Quicksort code, is that it is a little tricky to kind of, you know, so if you don't entirely understand choosing this random integer in this sequence, don't worry about it too much. I mean, the idea is to pick a random index that's between low and high inclusive, you know, that it could conceivably be low, it could conceivably be high. So we pick some spot, you know, where that's going to be where the pivot is. So I'm going to set the pivot to be list of spot, because that was the idea, is that we picked a random index. That's our pivot. So that's what we're going to use for our pivot value. I'm going to do something that I kind of don't want this pivot to be in the middle of this range of things. I want to kind of know where it is. So what I'm going to do is I'm going to do a swap where I swap what's in the low index with that spot. So I'm going to put the pivot right here. I'm basically putting the pivot into that beginning of this. So that I know where it is, so I can refer to it if I need to. I'm going to be rearranging things, so I kind of don't want to be rearranging the pivot. All right, now what? Now we want to do our partitioning task. So kind of the question is, we need some kind of a loop that's going to split things into two. This, it turns out to be a place where it's nice to use what is known as a loop invariant. There are different approaches to intro computer science. There are instructors, particularly a group of instructors who were teaching at Cornell, who tried to convince the community that the way we should teach intro programming is by teaching you to write your loops always using a loop invariant. That turned out to be a minority opinion. You know, they taught their course that way. They liked the results. Most of the rest of us I thought it was an interesting idea, but we weren't quite sold enough that we would kind of introduce the idea of loop invariance for everything. But this is actually a place where I think the loop invariant really shines. I think that if you choose the right loop invariant, you can kind of see, and you know, and this is what the people who advocate this approach would argue, is that the code almost writes itself. That, you know, that if you just pay attention to the loop invariant, it almost gives you the code that you want. And I think that's kind of true in this case. So this is a nice place to show you a loop invariant. So I have a picture here. What did I have? I guess I should have shown this to you earlier. I'm not sure why I kind of skipped this. But this idea is that I want to, you know, the partitioning is to partition into things that are less than or equal to the pivot, things that are greater than the pivot. This is where we want to end up, is that, you know, we want to kind of split it into the things less than or equal to the pivot and greater than the pivot. Tony Hoare is the computer scientist who came up with Quicksort. And I showed you this quote before. When we first went into linked lists, I pointed out that Tony Hoare is not a fan of linked structures, like linked lists, and we're going to be doing binary trees soon. Tony Hoare would not be a fan of binary trees either. So anyway, it just was, you might be interested that was his opinion. He would have loved. He's an arrays guy. He likes arrays, things that are in kind of a predictable place in memory. So I think it's. Let me see. Oh, I guess it's in this file Quick3. That's where I have some things. So what do I want to do for the invariant? Well, I want to think about where I begin. So initially, I have a set of values that I know nothing about. I mean, I don't know whether they're less than the pivot, whether they're greater than the pivot. I kind of don't know. And I want to reach a point that matches that picture that I just showed you right here. I want to have the things less than or equal to the pivot, you know, at the front of the array, of this sequence, and then the things that are greater than the pivot. So I want to reach a point where I've got the things less than or equal to the pivot and things greater than the pivot. So then the question becomes kind of what's a good intermediate state? And so this is, actually let me show it to you in this form first. So this is a way of thinking of the intermediate state, is that, and this is my loop invariant. What this picture that I'm drawing here is, and the idea of an invariant is that it's a relationship that I'm going to maintain on every iteration of the loop. So invariant means it doesn't vary. I'm going to want to make sure that it's true initially, and I want to make sure that no matter what I do inside my loop, I always get back to making sure that the invariant is still true as I come back around and begin another iteration of the loop. So it's something that I want to have always be true. And it's not easy to know what loop invariant to use. So kind of picking the invariant, there's some judgment involved there that's not obvious. But so I've kind of done it for you, or for us, which is, this is the in-between state that I want to identify. Is that I want to kind of partition these things into what will be three regions. Things that are known to be less than or equal to the pivot, things that are known to be greater than the pivot, and then things that are unexamined. So initially, everything is unexamined, and in the end, I want everything to have been examined and to have been put this way or that way. So I kind of am starting here, ending here, and this is the in-between. Is that some things are known to be less than or equal to the pivot at the front, some things are known to be greater than the pivot at the end, and then there are the unknown ones in the middle. That's kind of that's what I want to maintain. There's an interesting variation. If I had time, I'd show it to you, where another invariant that's sometimes used for this that can lead to a quicksort that performs better under certain circumstances is to have an extra region where you have a middle group that are known to be equal to the pivot. So if you know that if you think it's going to be common that you have a lot of ties, a lot of things that are equal to each other, then that can make sense then to kind of do a better partitioning into three known sequences, strictly less than the pivot, strictly greater than the pivot, equal to the pivot. Here what I've decided to do is to put things that are equal to the pivot into that first partition. So that's less than or equal to the pivot up there, greater than the pivot down there. Now, I was kind of hiding the fact that I have this little index 1, index 2 here. I want to introduce a couple of variables that keep track of the beginning and end of that question mark region. So those are local variables I'm going to use as a way to keep track of where does that question mark region begin and end. Notice this is different than low and high. Low and high are the entire thing, right? The low and the high are keeping track of the entire sequence of values. This is kind of a middle thing relative to that. It's keeping track of just this kind of these unknown values here. All right, so that's the invariant. That's the picture that I'm going to be looking at every time to try to make sure that I'm satisfying that picture. So if you think about it, take a look at the initial situation. Initially, everything is unknown. What would be values that you could give to index 1 and index 2 that match the initial situation where you know nothing? What could you set index 1 and index 2 to in order to kind of have it satisfy the initial thing? Well, initially, you don't know anything, right? So initially, you just kind of move index 1 and index 2 out to their extremes. So what I'm going to do is I'm going to set up an int index 1 and an int index 2. So one of the things you could do is you could just say, well, let me set that to be low, and let me set that to be high. Let me just kind of scooch them all the way out. Everything is unknown. Everything is in the unknown region. Certainly that would do that. Setting it to low and high is a way of saying that this is empty and this is empty. I've scooched it all the way out so that everything is in the question mark region. And that's kind of my initial state. So that's the invariant picture is allowing us to see how to initialize index 1 and index 2. I want to do something a little better than this, slightly better. We can, there's something that I've mentioned. We can do a little bit better. It's not quite true that everything is unknown, because remember what we did is we put the pivot there at the front. We swapped the pivot value into that initial spot. That was what we did with this call on swap, is we put the pivot at the front. So actually we know that the pivot is right there, and the pivot belongs in the less than or equal to pivot partition. So actually the pivot is where it belongs. It's in the correct partition. So we can do slightly better than setting index 1 to low. We can set it to low plus 1, because the pivot is in index low, and it's where it belongs. Okay, now that's kind of using the invariant to get our initialization. Index 1 and index 2 are all the way out, other than the pivot value at the front. Now we're trying to get to this picture. We're trying to get to the point where there's no unknown region. So what are we going to do? Index 1 and index 2 have been scooched out to the kind of the extremes. We're going to want to bring them closer to each other, closer and closer and closer. And so eventually we're going to reach a point where index 1 and index 2 are on top of each other, where index 1 and index 2 would be equal to each other. That's a pretty good place to get to. What that would mean is that if index 1 and index 2 are equal to each other, there would be exactly one question mark left, one thing left in the question mark region if they're equal to each other. But remember, we kind of talked about this in the Friday lecture. We actually want index 1 and index 2 to cross. We want them to kind of cross each other, so that that's how you make the question mark region empty, is by having index 1 cross index 2. So what I can say here for my loop is while index 1 is less than or equal to index 2. So while they haven't crossed, while the index 1 and index 2 haven't crossed, there's still a non-empty question mark region. I want to get to the point where the question mark region is empty. So that's this situation, is where index 1 and index 2 have crossed. While they haven't crossed, I want to get closer to being done. How do I do that? Well, I want index 1 and index 2 to get closer to each other. So I either want to bump up index 1 or bump down index 2, or both of those things. Well, so I've got a little picture here. So thinking about, so it matters a lot. What's that first thing in the question mark region? What's the last thing in that question mark region? Man, I really miss the audience, because it's fun to have the audience answer questions like what I'm about to ask. What would be a convenient value to find right there at list index 1? What would be a value that would kind of make my task pretty easy? The answer is, it would be nice to find something less than or equal to the pivot. Because if I find something less than or equal to the pivot, then this thing is where it belongs. It's kind of in the right spot. It's in the partition that it's supposed to be in. So I can say if list index 1 is less than or equal to the pivot, then it's where it belongs, and I can do index 1 plus plus. Okay, what are the other possibilities? Well, what about this? What would be a convenient value to find there at list index 2? Well, wouldn't it be nice if this was greater than the pivot? Because if it was greater than the pivot, then I could just scooch index 2 down by 1. So I can say that. Else, if list index 2 is greater than the pivot, then it's where it belongs, in which case I can do index 2 minus minus, right? I scooch it down, because that, I kind of expand the greater than pivot region by scooching index 2 down by 1. So those are two possibilities, that this value is where it belongs, or this value is where it belongs. What if it's neither of those two cases? Well, then what that means is that I have something over here that belongs at the end, over here, and I have something over here that belongs over here. So, if neither of them are kind of next to the partition where they belong, then they belong kind of in the opposite spots. So swapping them is the right thing to do. Swapping them will kind of put them into the spot where they belong, so that I can say, else what I would do is to swap index 1 and index 2, to put two things into their correct spots. And then what would I do with index 1 and index 2? I would do both things. I would increment index 1 and I would decrement index 2. I would do both of those things because I've put two different things into their correct spot. I've reduced the question mark region by two things by putting them where they belong. So that was that case where the thing at the front and these two different question mark things deserve to be switched in location. In which case, then we expand both this region and this region by bumping up index 1, bumping down index 2. Now, some of you who like to use plus plus and minus minus in expressions might know that you could actually do the plus plus here and you could do the minus minus here, and that would work because it actually would pass as a parameter the old values of the index, and then when it was done, it would increment in the one case and decrement in the other. So you could even write it as one line if you wanted to. I prefer to kind of make it very clear that this is being done after the call on swap. So I kind of prefer it this way, but it's really short if you do it the other way. One line of code. So this may seem surprising, but we're done. I mean, we finished kind of writing the partition code. And I think that you might say to yourself, well, I'm not convinced. And I think if you feel like you're not convinced, then those people who advocate for teaching this approach would say, well, see, Stuart Regis hasn't kind of taught you what you need to know to understand how loop invariants work. Look, I have maintained this relationship throughout. I've made sure that picture always holds at the end of it, or at the very beginning and at the end of every iteration. So I've kind of made sure that's true. I've got these variables index 1 and index 2 that are integers, and I'm either increasing the one, decreasing the other, or doing both of those things. So they're getting closer to each other, and they're integers. You can't have two integer variables get closer and closer to each other and not have them cross at some point, because, it just can't go into an infinite loop. Integers, there's only so many values to work with there. So it's going to cross, it's going to reach a point where this question mark region is empty, and we're going to end up in the final position. So the loop invariant really did inform how to write the code, how to initialize index 1 and index 2, what test to use, and what update to use. It kind of, the invariant, understanding the invariant kind of led us to see what code to write in all of those different cases. Let me hit compile to make sure that I haven't introduced a compiler error. And I did, I just forgot to have a semicolon at the end of that line. Let me see, so let's go ahead and compile. Well, when I call swap, I have to pass it the array and tell it the two different indexes. I did it right there, it looks like, but I hadn't done it right in the other spot. Maybe some of you noticed that before, but you didn't have a chance to tell me. But so I think now this is actually correct, but there's an issue that comes up that we need to talk about. So suppose that, you're asked, so suppose I'm writing the sort code. That's my job, so I'm supposed to write this. And I am going to call partition. That's going to be part of what I do, is I'm going to rely on the partition code. So suppose you're doing the partition task. I'm the sort, you're the partition. So I ask you to do the partitioning. So I know that you've picked a random spot in that sequence, you've used it as a pivot value, and you've split things into things that are less than or equal to the pivot and things that are greater than the pivot. So I know you've done a partitioning, but I don't know what pivot value you chose, and I don't know these ranges. So I don't know where this boundary is. So kind of what are the ones that are less than or equal to the pivot? What are the ones that are greater than the pivot? I need you to tell me that information somehow. So I need you to give me back some information about this. So we're going to change this. We're going to have this be slightly different. It's not going to be a void method. It's going to return an int. And I want to do something slightly different. Here. I have a kind of a final state. You know, I mentioned in the final state, you know, I want the two partitions. I'm actually going to do something slightly different, which is that I want the pivot to be in the middle. So I want to put the pivot where it belongs. So, you know, we're going to have the things greater than the pivot here, things less than or equal to the pivot here, but the pivot value itself, I want it to be here, and I'm going to return the index of that, the index of the pivot that I've put there in the middle. So how do I do that? Well, I know that the pivot is in this sequence right here, and I know that it's sitting at the front, so that I know that it's at the index low, okay? What's the index of this right here? The last spot. I want to kind of put it in the last spot of the, you know, kind of switch it with whatever's at the end there. Well, if you remember, I had the index 1 and the index 2, and the index 1 and index 2 crossed, so that highest index of this pivot is actually given by index 2, because index 2 crossed index 1. Index 2 is going to be have that index right there. Index 1 is going to be this index right here. So the index, the spot there is index 2. So what I'm going to do is I am going to swap. Let me go here. Swap in my list where the pivot is currently at the low position with index 2, where it belongs. You know, where I want it to be at the you know, at the end of that partition that has the things less than or equal to the pivot, and then I'll return index 2. So I'll let the person who called this method know that's the dividing line. That is the index of the pivot itself. And the things that come before that index are less than or equal to the pivot value. The things that come after are greater than that pivot value. But that's the index of where I put the pivot. That's kind of what I'm going to let this other code know. We're going to write this sorting code in a recursive way. So we saw kind of something like this with the merge sort as well. When would we know that we have actual sorting to do? Well, we have a low and a high. If low and high are equal to each other, then there's only one value to be sorted. And if they've crossed each other, then it's empty. So how do you know that there's at least two things? Well, that would be low being less than high. If the low is strictly less than the high, then there's at least two things involved. And so I'm going to say here, if low is less than high, then there's at least two things. And so we are going to make a call on partition. We'll finish this in a second. And there's kind of an implied else. There's nothing left to do. Otherwise, it's a one-element list or a zero-element list, and so there's nothing to do. So I'm going to call the partition method, and I'm going to remember what it tells me. So the pivot index is going to be what I get by partitioning the list, you know, that range, low to high. Then what am I going to want to do? I'm going to want to sort from low to the pivot index, and I'm going to want to sort from the pivot index to the high. I'm going to want to sort the two parts, you know, so kind of sort what comes in front, sort what comes in back. And the pivot index is telling me kind of that spot in the middle. This isn't quite what I want to do, though. Remember that, I mean, one of the things to be careful about is that we want to know that our recursive call is dealing with something simpler than the original. And if we do this, there's going to be cases where it won't be simpler than the original. If it's chosen a bad pivot value and it didn't end up partitioning, then they're not simpler than the original. What you want to do is take advantage of the fact that the pivot itself is in a correct spot. It's got the things that are less than or equal to it in front of it. It's got the things that are greater than it after it. So it's, no matter what, you know that you've got the pivot where it belongs. You've put at least one thing into its correct spot. And it's important for the recursive method to know that it's done at least that one thing. So this region to be sorted comes before the pivot index. And this region to be sorted comes after the pivot index. So what I want to do is sort from low to pivot index -1. I don't have to sort the pivot index itself. And here I can start at pivot index +1, because the pivot itself, the thing at pivot index, is in the right spot. And so that way, these two partitions are each at least one shorter than the original. So that the recursion, we believe, should work. Well, let's try compiling. And I didn't. I didn't include my parameter. Why I'm forgetting to include my array, I don't know. Sort my list from that to that. Sort my list. Okay, let's try compiling, and let's try running the code. And so it's going to compare against the built-in sort, which also uses a quicksort. We're at 1.559, about a little less than 1.6. So 56%. We're within 56% of the built-in sorting routine, arrays.sort. That's pretty good, I think. Given the one lecture's worth of material, and the lists match. So it verified that we did it correctly, and that's Quicksort. That's kind of how Quicksort works. I want to say a little something about the stable sort. So let me repeat something that I said last time. So I had this example where I had some names of people, and I had kind of what class they are. Are they one for a freshman, two for a sophomore, and so forth? Actually, maybe what I'll do is sort by that column first, because you're going to see that what it's going to do is there's a bunch of freshmen here. Grace Hopper is a freshman, Alonzo Church, Ada Lovelace, and John von Neumann are freshmen. So if I sort by them, you're going to see that they're in an order where, so all the freshmen are grouped there at the top, but notice that their names are not in alphabetical order. Well, if I came over here and I did a sort by name, I've put all people, all of them are ordered by name. They're all alphabetically ordered now, and they're not ordered by what year in school they are. But notice if you go through here, if you look at the freshmen, Alonzo Church is here, and then Grace Hopper, and then Ada Lovelace, and then John von Neumann. They are alphabetically ordered, but they're tied in the sense that they're all freshmen, right? So that if I go here and I do a sort again by this column, then it's got the four freshmen at the top, but notice that it preserved the alphabetical sorting. It preserved the relative order of these four values, and that's called a stable sort. So it's letting you know that it's a stable sort. Over here in the Quicksort, when we're doing this thing where we're swapping things, that come later and then moving them earlier, that destroys the stable property. Quicksort is not a stable sort, so it does not preserve that property. It's kind of interesting. I was looking at the description in the Java class libraries and in .NET. In the arrays class, it talks about things. It says an interesting comment here. I think this is something that I've seen you guys struggling with all quarter, and we struggle with it too a little bit. Do you talk about the implementation or don't you? Sometimes people want to know. They say the documentation for the methods contained in this class includes brief descriptions of the implementations. So they feel a little guilty, right? You shouldn't be talking about the implementation. We take off points if you talk about the implementation. Such descriptions should be regarded as implementation notes rather than parts of the specification. So they're kind of saying, well, don't really consider that part of the documentation. Implementers should feel free to substitute other algorithms so long as the specification itself is adhered to. For example, the algorithm used by sort of object does not have to be a merge sort, but it does have to be stable. So they include kind of that idea of it being a stable sort. In the .NET description of the sort routine, there's a bunch of different remarks here, and it mentions various things. It mentions down here, this implementation performs an unstable sort. That is, if two elements are equal, their order might not be preserved. That's because they do use a quicksort. They link to it here, that they actually use a quicksort to do this. It has to do with the swapping that we're doing here. You could think of it as, suppose that there's a freshman that comes later in the list, You're going to, and you might swap that to the front when there's some other freshmen that are not going to be moved, because we're going to kind of bump up our index 1 without swapping. And so that's why we don't preserve the order of things that are equal. In our merge sort code, we were very careful to make sure that we preserve the relative order. We're about to get cut off, so that's all that I want to talk about today. We'll do real material on Wednesday for the next homework assignment.